Assalamualaikum warahmatullahi wabarakatuh, and salam sejahtera to everyone. So we are moving to the part 3 under soil compaction topic. Okay, previously we already discussed on the methods to be conducted at laboratory. Means that how to conduct compaction tests in the lab. So remember, we have two methods, okay, for lab. Okay, we have a method based on the standard proto, and the other one is modified proto. So when talking about laboratory testing, compaction is known as proto test. Okay, it's just that you have to identify whether you carry out it based on standard or based on modified proto test. So now we are moving to field testing. Okay, we are moving to field testing. Okay, I'm sorry, this is actually not the field figure. Okay, this is actually lab. All right. Most of the compaction in the field is done with rollers. So the four most common types of rollers are smooth with rollers, also known as smooth drum rollers. We also have pneumatic rubber tired rollers, and also sheep foot rollers. Okay. And we also have different type of rollers, which is rammer, vibro tempers, and also compactors. So this all rollers that has been mentioned is actually divided into two groups, namely heavy compactors and also lightly compactors. Okay, for light soil compacting such as rammer, vibrating plate compactor, and also vibro tempers, they normally use for soil that compact the small areas only. Okay, only covers the small areas, and where the compacting effort needed is less. Okay, their features are normally alike and can be hand or machine operated. Okay, so it's easily to be to bring those small machines to the site. Okay, meanwhile for heavy compacting machines, okay, for heavy compacting machines such as smooth wheel rollers, pneumatic rubber tire rollers, and also sheep foot rollers, they are used for large area, okay, and for use also on different types of soil. The heavy compaction equipments are selected based on moisture content of soil and types of soil. Okay, for example, when you're talking about smooth wheel rollers, normally for smooth wheel rollers, we use it for graded sand, gravel, crushed rock, asphalt, okay, where the crushing is required. Okay, they are used on soil which does not require great pressure for compaction. So these rollers are generally used for finishing the upper surface of the soil layer. And these rollers are not to be used for uniform sand. So normally this is for gravel type of soil, okay, where we need a very light surface finishing. Okay. On the other hand, for pneumatic rubber tire rollers, okay, pneumatic rubber tire rollers are also called as rubber tire rollers. These rollers are used for compactions of coarse grain soil, okay, with some fines. Okay, it is specifically for coarse, okay, with a little bit of fine, okay, but just a few. Okay, but the main type of material still are coarse grain soil. So, and this roller also less suitable for uniform coarse soils and rock. Okay, and generally pneumatic tire rollers are used in pavement subgrade works, both earthwork and also bituminous work. Okay, so this is not suitable. Okay, this one is not suitable for uniform types of coarse grain. So it's not suitable. Okay, it's not suitable. Okay, they can be used for coarse grain material with some fines. Okay. Okay, the last one for heavy compactors is sheep foot rollers. So you have sheep foot rollers. Okay. So you have sheep foot rollers. Okay, sheep foot rollers are used for compacting fine grain soil such as heavy clays and silty clays. Okay, so this one is opt for fine. This one is for fine. This one just now is for coarse with some fine. Okay, and this one is most likely is for big particles lah, gravel or the uniform coarse grain soil. Alright. Sheep foot rollers. Okay, come back to sheep foot rollers. Sheep foot rollers are used for compaction of soil in dam, embankments, subgrade layers, in pavement, and also for railroad construction. So these are the examples of smooth wheel rollers, pneumatic rubber tire rollers, and this is for sheep foot rollers. Okay, so remember what are the function of all those three heavy compacted soils. Okay, one is for most likely is for uniform coarse grain material, and then you have pneumatic is for coarse grain soil with some fines, and sheep foot rollers are the heavy compactors. Okay, purposely for fine grain soil like heavy clay. Okay, anything with a fine grain materials. Okay, which means that the domain particles are fine grain material. Okay, in most specification for earthwork, the contractor is instructed to achieve a compacted field dry unit weight of 90 to 98%. So this is based on the specification. Okay, 90 to 98% of the maximum dry unit weight, also known as maximum dry density. Okay, determined in the lab by either standard or modified proto. So remember I told you initially what you have to do is, okay, when you went to any construction site, okay, at the area that to be compacted, it means that it's not been compacted yet. Okay, it has an intention to be compacted. So what you have to do is to get the sample from that area and bring to the lab. Okay, bring to the laboratory, and you have to test it. Okay, you have to test it. Okay, it doesn't matter you test it based on the standard or modified proto test. The procedure is just same, but there's some specification of features that are different. Okay, so you got the results from the compaction test at lab. So from the lab testing, you will determine the maximum dry density and also optimum moisture content. So that's are the things that you have to determine in the lab. So whatever the results you have in the labs, okay, would be the guidelines for field. So will be the guideline for field. So what are the guidelines, okay, to be satisfied at field is whatever the dry unit weight or the dry density that to be achieved after compaction must be meet this requirement, which means that it must be within this value. Okay, must be within 90 to 98% of the maximum dry unit weight or dry density that you already obtained in the lab. Okay, and it is measured based on the value of relative compaction. So it is measured in terms of relative compaction. So this is a relative compaction, R in the percentage. Okay, and as shown by the given formula. So this is the formula given, okay, where R is equal to dry unit weight, or if you use dry density, it means that you're using dry density, okay, obtained at field divided by dry unit weight you obtain at lab or dry density. Okay, and the dry density you're talking about here is maximum dry density or maximum dry unit weight. Okay, obtained in lab. Okay, so you got this value, then you can calculate the value that supposedly obtained at field. So for example, like the maximum dry density, okay, obtained at lab is about 2000 kilogram per meter cube, and the specification, okay, is already stated that it must whatever density obtained after compaction at field must be within these two, within this number. Okay, 90 to 90%. Okay, let's say we want to make sure that the R is equal to 90%. So it means that the maximum dry density at field, okay, to be obtained must be 90%, at least 90% from 2000 kilogram per meter cube, which means that it has to achieve at least 1800 kilogram per meter cube. Okay, how about if they not meet this minimum requirement, which means that that area need to be compacted again. Okay, the area at fill has to be compacted again until they reach this requirement. Okay, there are several methods that can be applied to determine the field density of soil at site. Among them are sand cone method, rubber balloon method, and nuclear method. However, in this course, we will only discuss further on sand cone methods. Okay, we only discuss on sand cone methods because of why? Because that has been practically applied at field. Okay, most likely. Okay, if you want to know further on the rubber balloon method, nuclear method, and other method, please do your own reading. Okay, it's just that for this course, for field testing, we only going to discuss in details on sand cone method. Okay, this is the sand cone method device and also procedure to be discussed. Okay, the sand cone device consists of glass or plastic jar. Okay, you have glass or plastic jar with a metal cone attached at its top. So you have a metal cone here attached at its top, and you also have the glass or plastic jar, okay, with a metal cone attached at its top. Okay, here are the procedure of sand cone method. Okay, the procedure are as follow. So the first thing that you need to do is, okay, you need to weigh the jar, the cone, and the sand filling the jar and determine it as W1. So if let's say you weigh in gram or kilogram, which means that this one will be mass number 1, denote as M1. So and then you are moving to the side. Okay, so let's say this is your side and this area has been compacted. So this is the compacted area. Okay, what you need to do is to excavate a small hole. Okay, you need to excavate a small hole, okay, from the area that has been compacted. From the area that has been compacted. Okay, you excavate this area. Okay, so and then you weigh. Okay, weight of the moist soil excavated from the hole. Okay, and denote is as W2. Okay, denote is W2. So you take the sample from this area. Okay, you weigh it and denote it as W2. Okay, and you determine the moisture content. So you determine the moisture content. So you determine the moisture content, which means that you take a representative of sample from this area. Okay, from this small hole. Okay, put into the container, weight it, put into the oven. The next day you determine the moisture content. So once you already know what is the first thing that you know just now from this area is the mass of compacted, right? Mass of compacted sample. Okay, mass of compacted, and this compacted sample, because it has been compacted, so definitely it is the wet condition, because during compaction you fill, okay, that area with water. Because of what? Water is a helper, okay, to facilitate the movement of the soil particles, okay, and rearranging back the soil particles from loose to soil. So this area, okay, the one that you denote as W2 just now, okay, you already know what is the moisture content in the next day, so you can calculate the dry. You can calculate the dry weight of the soil, okay, which you denote as W3 by using this equation. So this is actually quite similar to if you want to find dry density. Okay, you have bulk divided by 1 plus W. Okay, what is bulk? Bulk is the density in moist. Okay, moist or wet. What is here? This is the density in dry. So it's actually the same thing, because you are talking about the same volume. Okay, if you divide this one with B and you divide this one with B, so this would be rho bulk and this would be rho dry. But since now V is consistent, so it can be cancelled out. And the next step is the cone will send fill jar to its inverted and place over the hole and allow the sand to flow out into the hole. So this is your sand cone jar. Okay, so here are the place that has been compacted, and you already excavate this hole, right? Okay, you excavate this hole. Okay, you already excavate this hole, so this area will be empty. Okay, let's say you already excavate this hole, so there's a hole here. Okay, so you put the cone here, then maybe the jar is here, you cone here, so you open this one, so you allow sand to fill up this hole. Okay, you allow sand to fill up this hole, so it means that you open the inverter here, so you allow the sand that filling the jar initially, okay, to flow out into the hole, right? So the weight of the jar, cone, and remaining sand in the jar will be determined as W4. So in order for you to calculate the weight of sand to fill the hole and cone only, which means that you are just looking on this area only, okay, you want to look at this area only, W1 will be minus with W4. W1 just now is what? The weight of jar, cone, and sand, right? Jar plus cone plus sand. This sand is in the jar, okay? And W4, what is the W4? W4 is the weight of jar, cone, and remaining sand. Okay, remaining sand in the jar. So now you want to know, okay, W5 is the weight of sand to fill the hole and cone only. So that is why you minus W1 minus W4. Okay, the volume of the hole excavated can now be determined by using these equations. Okay, V, let's say this is meter cube. Okay, sorry, meter cube, and this one, let's say you are using kilonewton per meter cube. Okay, so because it's you use weight, so that will be kilonewton. Okay, so the volume of the hole that has been excavated, so the hole that has been excavated here, we want to know what are the volume, can be calculated by using this one. Okay, first you need to know the weight that fill the cone only. Okay, the weight that fill the cone only, that is a what? W5 will minus with weight of cone, because what is W5? W5 is the weight of sand in the hole and cone. So you minus with WC, you minus with cone, so means that you can get the weight of hole. Okay, weight of sand filling the hole. Okay, and divide by dry unit weight of Ottawa sand. Okay, this one has been provided. Okay, this one is being provided. Remember, we fill up the jar with sand, and that sand is the Ottawa sand. So the supplier will provide you with the dry unit weight of that particular soil material. Okay, so it means that this one is already given. So by using this equation, you obtain the volume. Okay, the volume of the hole. Okay, so your intention is to get the maximum dry weight, okay, of the area that been compacted. So what are the area that been compacted? Is this area. Okay, it's definitely this area. Okay, the area that has been excavated just now. Okay, so using the same equations, okay, dry unit weight is equal to dry weight divided by volume. The dry weight is already obtained, okay, initially in the first step. Okay, divide with the volume here, then you get the dry unit weight. That's it. So what you have to check later is you need to check whether this dry unit weight that you achieve, okay, after being compacted must meet the requirement, which means that the relative compaction must be at least 90 to 98% from the maximum dry unit weight you obtain at lab. Alright, so you already finished watching the video. I hope that it can give you better understanding by watching that video. But for information, that video is not prepared by SKA students. Okay, I just get the video from the YouTube So thanks to them, okay, thanks to those who have made the video, okay, and made our life easier. All right, so let's refer to this example. The given informations are as here as follows. Dry unit weight of Ottawa sand is 104. Okay, it is dry unit weight. Suddenly use the mass here. It's not dry unit weight lah. It's supposedly dry density. Okay, here is dry density. Okay, dry density, because we are using mass here. Okay, same thing also is not weight. Everything you have to correct it is not weight. It is actually mass. Okay, this is also mass. This is also mass. Okay, mass of Ottawa sand to fill the cone is 0.25 kg, 58 kg. So this one is mass of cone lah. Okay, and dry unit weight of Ottawa sands. Okay, it's a dry unit weight of Ottawa sand. This is dry unit weight. Mass of cone sand before use, so this one is M1. Mass of jar, cone and sand after use, this is M4. Mass of moist soil from the hole itself only, then this is mass of hole lah. Okay, alright, so the moisture content, okay, from the compacted area, this is from compacted area. Okay, been determined as equal to 11.6%. So okay, alright, this is also wrong. It's not supposed to W everything. You have to correct into mass. Okay, okay, the next step is you need to calculate the mass of the sand to fill the hole and cone. Okay, and by using this given calculated procedure, this is actually your M1, this is your M4. So M1 minus M4, you've got M5 here. Okay, you've got M5 here. Okay, what is M5? M5 is actually the mass of what? The mass of sand in the hole plus cone. Okay, so that's the reasons why you need to minus. Okay, if you want to know the mass of sand to fill the hole only, you need to minus this value, okay, with the mass of cone, then you got this one. But if I'm not mistaken, there's some mistake in the previous slide. Okay, because in the previous slide they already give you the mass of sand in the hole, right? The mass of the sand in the hole. Okay, so supposedly you don't have to minus that value, or maybe my mistake. Okay, maybe it's already calculated there. Okay, it's okay, you please double check that one. Okay, and then calculate the volume of the hole, okay, while using these equations. Okay, and this one you can obtain, okay, once you excavate the hole, okay, get the moisture content, you can calculate the dry mass, okay, of the sample that has been compacted, and finally get the dry density. Okay, everything needs to be corrected. This is not dry unit weight, this is dry density. This is also not weight, this is mass. Okay, please correct everything. Okay, and finally you got this value. So yeah, the dry density at fill is equal to 100.77 kilogram per meter cube. And what's the things that you have to check later? Okay, you need to check in terms of the relative compactions, either it meet the specific requirements or not. If it's not meet the specific requirement, remember what you need to do? Recompact back that area. Okay, let's discuss on the several factors that affecting the compaction characteristics. Okay, here are some of the factors. Okay, but remember, it is not only limited to these factors that we're going to discuss after this. Okay, there are also some other factors, but for this course, we will only discuss on these three factors. Okay, what are that? Okay, among them are moisture content, soil type, and the compaction effort. Okay, look at the effect of moisture content first. Okay, look at this figure. Okay, we have three types of compaction curve here. We have type A, we have type B, and also have type C. Okay, I indicate it with a different colors there. Okay, for type A, the curve is black color. Type B, the curve in red color. And the type C, that curves. Okay, we have two curves there. denotes in blue color. So if you look at those curve, okay, for type A compactions, okay, it's already stated that are those that have a single peak. Okay, those that have a single peak. If you look at here, you only have single peak, so you can figure out what's are the single peak there. You can figure out the significant peak point here. This is your maximum dry density. Okay, and normally the sample or the type of material associated to this kinds of curve, also known as bell-shaped curve, okay, because we also say that it's a bell-shaped curve, okay, where they have a liquid limit between 30 to 70. Okay, meanwhile for compaction curve on type B, okay, compaction curve on type B here do not have a definite peak. Okay, you don't have the definite peak. It's very difficult for you to find what is your maximum dry density because you don't see the peak value. There is no significant peak value. And normally this kinds of curve, okay, is associated to a soil with a liquid limit greater than or about 70%. Okay, greater than or about 70%. Okay, they may exhibit the compaction curves of type B. Okay, and such soils are not very common. Okay, curve type C are 1 and 1/2 peak. Okay, you have one peak here and you have another one peak here. Okay, so here, okay, what we call it as 1 and 1/2 peak, and it's a double peak curve and also have a double peak curve. Okay, compaction curve type C can be found for soil that have a liquid limit less than 30%. So which means that you're talking about factors that are affecting the soil compaction characteristics. Okay, with regards to moisture content, it's normally related also with the type of soil. Okay, the type of soil. Okay, next we discuss on the compaction characteristic that been affected by soil type. So when you're talking about soil types, okay, we also referring to what? We refers to grain size distributions. We also refers to shape of the soils, okay, the specific gravity of soil solids and the amounts and types of clay mineral. Okay, the amounts and types of clay minerals. So it means that you're talking about the clay minerals here, means that the clay, okay, in a small amounts or big amounts may have influenced, okay, may have influenced the overall behavior of the soil. Okay. Okay, all of them have a great influence on the maximum dry density and also the optimum moisture content. Okay, for most clayey soil and soil consists of both coarse and fine grain material, note that the bell-shaped compaction curve is typically, okay, you can refer to curve 1 and 2. Okay, this is most likely, okay, will be experienced by fine grain soil, okay, with both and also fine grain soil. Okay, for example, like this one, we have sand and also silt. Sand is your coarse grain soil and silt is your fine grain soil. You also have silty clay like this. Okay, so it is silts for fine grain soil, clay for also for fine grain soil, but silty here is the size is more or less can be also like sandy soil. Okay. On the other hand, cohesive soil with high plasticity will have a tendency, okay, to have lengthy curve on the left side prior achieve its optimum moisture content. Okay, refer to curve number 3. So this is curve number 1, this is curve number 2, this is curve number 3, and this is curve number 4. So curve number 3 just now, okay, they say that it is normally typically for soil, okay, types of cohesive soil or fine grain soil with high plasticity. Okay, with high plasticity, the pi value is high. Okay, when talking about pi value, it means that you are referring to fine grain soil. Okay, so fine grain soil with high plasticity value may have tendency of these kinds of curve. Okay, where you will see that they have a tendency to have a lengthy curve on the left side. So this is your left side, right? This is your left and this is your right. So that they have a lengthy curve on the left side before they achieve its optimum moisture content. Okay. And for sand, okay, or for coarse grained soil, the dry density has a general tendency first to decrease the moisture content. Okay. If you look, please refer to curve number 4 here. Okay, you are referring to curve number 4 here. Okay, this is normally associated for sandy soil. Okay, for sandy soil, where they will experience, okay, decrease. Okay, decrease in dry density. Okay, at initial moisture content, and then to increase to its maximum value with further increase of moisture. Okay, the last factors to be discussed that may affect the compaction characteristic, means that may change the compaction parameters, is compaction effort. So the compaction effort is an energy. Okay, when talking about compaction efforts, means that we are referring to energy. Okay, it's an energy used on mass of compacted soil for each volume. Okay, and the unit for compaction energy, okay, or compaction effort, is kilojoule per meter cube. And the basic equations based on the factors of number of blows, number of layer, weight of hammer, and drop of hammer for a given volume mole. So we have the example here, okay, comparing between the soil, okay, the similar soil that being compacted based on, the first one is based on standard proto and the second one is based on modified proto. For example, that we take the same type of soil material, okay, one we tested based on the standard compaction procedure, and the second one is based on the modified compaction procedure. Okay, so if you look at here, by using the previous equation that has been given, we can calculate the CA value for both standard and modified proto, and we'll see that the standard proto give a compactive energy about 584 kJ per meter cube, while compactive energy of modified proto is about 4 times higher. Okay, it's about 4 times higher. It's about 2653 kJ per meter cube. This is very clear, okay, and definitely because of why? Because of modified proto needs more layer. Okay, it needs more layer. We need more layer compared to only 3 layers for standard proto. Okay, and they also use much higher weight of hammer compared to standard proto here, and also fall distance also is higher than standard proto. Okay, so that's the reasons why, okay, a very significant increase in compaction energy for modified proto as compared to standard proto. Okay, another example of how compaction effort affecting the compaction characteristic can be seen in this figure. Okay, assuming that those curves are obtained for similar soil that has the same properties but been compacted in different number of blows. Okay, different numbers of blows. The rest is similar. It's just that you've been compacted on the same layer with a variations of number of blows. Okay, the first one is 20 blows, second one is 25 blows, increase to 30 blows and 5 blows. Okay, you will see that those the compaction effort is increased with increasing number of blows. Okay, it can be clearly seen also that the compaction effort is increased. That the maximum dry density of compaction is also increased. Okay, in addition of that, the compaction effort is increased, the optimum moisture content is decreased to some extent with the increasing number of blows. Okay, so you will see that the maximum dry density here, okay, the maximum dry density is increased with increasing number of blows. Okay, you increase the number of blows, okay, you increase the number of blows, the maximum dry density will be increased. Okay, and when you increase the number of blows, okay, on the other hand, the optimum moisture content is reduced. Okay, the optimum moisture content is reduced to some extent. So why this happen? Alright, remember, when you do a compactions, you need water. You need a water as a helper to help. Okay, as a helper to help. Okay, the process of compaction. Okay, the process of compaction. So let's say you increase the number of blows. It means that you already put some extra on certain factors. Therefore, you need less help from the water. Okay, you need less help from the water. So you don't have too much water to help the process because you already, okay, adding external help. Okay, you already add some external help. Okay, that is only an example. Okay, just to make sure that you understand the reasons why when you increase the number of blows, which means that you put more effort. Okay, you put more effort. Okay, the outcome, okay, the outcome is maximum dry density is increased. Okay, and you use less of help. Okay, this is actually the same thing happens to you if, let's say, you are doing household. Okay, you add something extra. It means that you bought a new vacuum. Okay, you bought a new vacuum, so the output is better. Okay, but the time to finish up the whole things, okay, to finish up, clean up your house is less. Okay, we already finished discussing on this module. Okay, the lecture number 3 under module soil compactions. This is the part 3. We have part 1 and part 2, which means that we already finished everything. So I hope that every one of you can understand very well my lecture, and I'll see you on the next lecture under next module. Thank you very much.